in string theory, there was always what people felt as an embarrassment, that the theory said there should be extra dimensions beyond the 3 spatial dimensions we see. There should be more, maybe 6 or 7 more spatial dimensions. Why don't we see them? Well, they'd have to be curled up really tiny so that even our best microscopes would not have detected them yet. And that's perfectly possible, but it wasn't really good for anything. It seemed like it was an annoying feature of the theory. We had to work to hide it. But there was also an annoying feature of reality that Joe Polchinski and I started thinking about 15, 17 years ago, which is called the cosmological constant problem. It's the fact that according to the best, very well-tested theories we have, they fail in one respect. They tell us that empty space should have an enormous weight. This sounds ridiculous, but it just comes out of the math. And you have to explain why that's not there. Why don't we see that? If it was there, even atoms would immediately explode from the gravitational consequences of this weight. It's a very strange kind of stuff, this empty space weight. It's called vacuum energy. And the cosmological constant or vacuum energy problem is the challenge of explaining why we see so little of it. In fact, there is a little bit of it, but it's an incredibly tiny amount. And so we sort of took these 2 problems, one theoretical with string theory, all these extra dimensions, and the real problem we faced in observation, why is there so little vacuum energy? And we thought, well, wait a minute, maybe they have something to do with each other. When you really think about how you can make empty space in string theory, it's not just by wrapping up 6 spatial dimensions that we're embarrassed about and don't want to see. You have a lot of choice about how you're going to wrap them up. You can tie them, if you will, into different kinds of knots, different kinds of what we call topologies. There are different ingredients that you can throw in, sort of like making an atom out of 2 neutrons and 4 protons or some other mixture. You have a lot of choices there. And so you sort of can make different mixtures of how you put together empty space. And when you work through the combinatorics, it's actually a huge number of choices. We found that it should be at least 10 to the hundreds of different possibilities. And if you have so many possibilities, then just by sheer luck, once in a while you'll have an empty space which weighs very little. Because essentially the weight of that empty space is put together out of many positive and negative large numbers which get added together. And once in a while they just happen to cancel by accident if you try so many times. And that's how string theory led us to take the multiverse very seriously. For one, it comes naturally out of the structure. It seems to be built into the theory. But I think more importantly, this is currently our only serious explanation of the cosmological constant problem. And I suspect that if a more compelling explanation were to come along, well, we would take that very seriously and we might be less interested in exploring the possibility of a multiverse. But this has been a very serious problem that has plagued physics for about half a century with almost no useful ideas whatsoever about how to deal with it. And so the fact that the multiverse that comes out of string theory helps with that problem. And by the way, not any multiverse, the one that comes out of string theory, is serious evidence, I think, that we should pursue this direction further.
The different ways that the laws of physics can be different from place to place are kind of like different phases that a material can be in. So we talk about water, for example, being solid ice, liquid water, water vapor. And the conditions are different, the speed of sound, the density, the temperature, and so forth. So one way you can have a cosmological multiverse is for space itself to be like that. Space-time can be in different phases where there's different numbers of dimensions, different coupling constants, different particles, and so forth. String theory gives us a way to make this idea a reality. If you believe in string theory, this is a prediction of the model. String theory just says that instead of particles, we have little loops of string, they propagate along, and when you take the quantum mechanical version of string theory, it turns out that the strings naturally propagate in 10 dimensions of space-time. So 9 dimensions of space, 1 dimension of time. We live in 4 dimensions of space-time, 3 of space, 1 of time, so 6 dimensions have to disappear somehow. And that can be done. This is an old idea, going back to Kaluza and Klein. You take the extra dimensions and you curl them up into a little ball. So the idea would be that there are 6 dimensions of space that are invisible because they're so small. But then you start asking, well, how many different ways are there to curl up 6 extra dimensions? It's not just a little sphere, it could be a torus or something more complicated. And the answer grows very, very large, very, very quickly. And we toss around estimates like 10 to the 500 different ways of doing it. But we don't really know whether that's a true number or not. That's just a back of the envelope estimate of how many different ways there are to curl up the extra dimensions. And every one of those ways implies different low energy physics, different sets of particles, fields, and forces. There are definitely differences. I mean, string theory doesn't predict that the multiverse exists. It sort of makes it possible. It makes it possible for different regions of space to have very different looking local laws of physics if the extra dimensions are compactified in a different way. So you can say that there's, in string theory, 10 to the 500 different possibilities. That doesn't mean they're actually out there realized, right? But inflation says that the early universe could start with a tiny little region of space. It can expand exponentially quickly. And different regions of space can then sort of fall out of inflation into different compactifications, into different ways those extra dimensions could be curled up into a little ball. That makes the universe real. So that's what's called populating the landscape. The string theory gives us this landscape of 10 to the 500 or whatever different possibilities. Inflation brings them to life. Maybe, we think, we conjecture that that is true. We're trying to work out on the basis of equations and formulas whether or not this is going to happen or not. The different scientists write papers going back and forth in different ways. But if it all fits together at the end of the day, the idea would be that string theory explains how there could be different regions with different laws. Inflation actually makes them true. So there can be, let's say, 10 to the 500 different ways the universe could be. Inflation makes an infinite number of pocket universes. That just means you make the same kind of universe over and over again.
Not necessarily CMB. One thing people talking about CMB is in the theory of the multiverse, if there are a lot of universes which could even collide. If the two universes collide, it can be seen in our universe as some signatures left in cosmic microwave background radiation. So if you see the structure of cosmic microwave background radiation very, very carefully, you might be able to see those signatures, if you're lucky, because the strength of the signatures depending on detail on the multiverse. For example, rate of producing a lot of different universes and so on. So we may or may not see it, but at least you could say the multiverse has testable signatures, and if you're lucky, you could get it. There are also a bunch of other ways that the multiverse theory can be tested, which makes the theory be a science, partly. Okay? And one of the things I kind of sorted out with Alan Guth was that the curvature of our own universe. In the current formulation of the multiverse theory, based on, say, stringish landscape and inflationary theory, eternal inflation, our own universe is regarded as one kind of bubble. We're living inside that bubble. And if that's the case, our space looks like negatively curved. What's the meaning of negatively curved? If you draw a triangle in flat sheet, the addition of 3 angles would become 180 degrees. But if you put the triangle on a surface of sphere, then because the shape is like that, so angle adds up to be bigger than 180 degrees, by which we mean the space is positively curved. And negative curve is the other way. The angle adds up less than 180. Now you can draw a big triangle using light in our own universe, and the multiverse predicts that that's negative. Unfortunately, we can't predict the size, how negative that is. So if the experiment see 180 degrees plus minus 0.01 or something, because experiment always has an error, we may not be able to conclude that the space is negative curvature, maybe tiny, tiny negative curvature. But if you see, for example, positive curvature in future experiment, by the way, this is a place where observation will improve 2 orders of magnitude, we expect, in next decades. So then if you see positive curvature, this theory can be excluded. Okay? So some people say the falsifiability is a criterion of scientific theory, which I don't completely agree, but even under that criterion, this theory is falsifiable in general. Okay? And if you see negative curvature, what happens? Negative curvature would be tiny, but still negative, because we already know the our universe is like flat, like at 1% level, namely deviation from 180 degrees less than 1%. So it's pretty much flat, but slightly negative. If you see that kind of thing in future observations, multiverse is a perfect theory to be able to explain that. And the detail is pretty much detailed, but in multiverse theory, you could imagine that your theory wants to make curvature more and more negative, but if it's too much negative, you are not there. Because negative curvature, highly negatively curved universe, no complex structure will develop that you can kind of compute. So that balance between the two effects will make curvature slightly negative. So that's what can naively happen. So if you see in future experiment, you see the negative curvature, that will be good suggestion of the multiverse and the good test. Of course, it's not proof. People often say that you have to be able to prove for the theory to be scientific. That is not really good criterion. For example, nothing about history can ever be really proved in the real sense that you went back and you really saw it. And you just postulate the theory and then study consequences. You keep testing whether those consequences are compatible with what you see. Okay? So it's never be kind of real proof in the mathematical sense. For example, do you really know that dinosaurs exist at the level of mathematical proof? If you say that my theory is UFO came and really made the bone of the dinosaur in such a way that it fools us, can you really disprove it? Nobody. But that theory requires same number of assumptions as the one you want to explain. So it's not the theory. So in that sense, we try to keep finding better and better theory in a sense that we can explain the same thing as the smallest ingredient and most simple naive ingredient. And the multiverse theory is the one which explains certain features of our own universe, including the cosmological constant, the smallness of cosmological constant. That's the theory. So you keep studying the consequences and keep testing that against observations. That's what we have to be doing.
So it has to be a slightly bended or a slightly hyperbolic shape.
Exactly, that would be really great signatures. On the other hand, as I said, we don't know how negatively our own universe is curved. So if the experiment or observations keep seeing consistent with being flat, that does not exclude multiverse at all. Because it's possible that our own universe may be slightly negatively curved. If that level is 0.00001, experiment would never be able to probe that, at least in the foreseeable future. So interpretation, you have to be careful. But if the sign is opposite, you can exclude it.
The real problem with testing the multiverse is, so number one, you don't test the multiverse. You test the theory that predicts the multiverse, right? Number two, the theories that predict the existence of a multiverse aren't that well developed yet. They're not that specific. They're sort of generic families of theories within which we can try to make predictions, but there's always free parameters. There's always things we don't know, numbers that could be very, very small. So I think that even if the multiverse ends up existing and being real, it's certainly possible that we will never know, that we will never be able to directly see it or even make a strong observation that convinces us it's real. On the other hand, we might be able to. There are parameters, there are versions of the theory where different universes bump into each other, different bubbles within our space-time bump into each other, and they leave spots, for example, on the cosmic microwave background, spots that people are looking for. They could be very, very faint, but maybe they're there. We can also test the underlying ideas of string theory and inflation. For example, inflation predicts that not only should we see perturbations in density in the universe at early times, which we have seen in the cosmic microwave background, we should also see gravitational waves created during inflation. Now recently, the LIGO experiment has detected gravitational waves, but not ones that were created during inflation, ones that were created 1 billion years ago when two black holes spiraled into each other. This idea that inflation in the first tiny fraction of a second created gravitational waves is a different idea that you have to test in a different way. We think the best way to test it is to look for the polarization signal of these gravitational waves in the cosmic microwave background. We haven't seen it yet. There was a little brief moment when we thought we had seen it, but that moment went away. So we're still trying. If we see those gravitational wave signatures in the polarization of the microwave background, it would be quite good evidence that inflation happened, And then if we can improve our theoretical understanding of inflation to say that if inflation happens, there is a multiverse, then we'll be able to conclude with high confidence that the multiverse is real. Well, we build mathematical models to make predictions. Certainly the microwave background and also large-scale structure in the universe is telling us a wealth about conditions in the early universe, which we can use to constrain our theories. Gravitational waves we found from black holes. We're trying to look for them from the very early universe. We're trying to directly detect the dark matter, right? We think that there is dark matter particles. We don't know what they are, so we're trying to find them directly. We're trying to study the dark energy of the universe that is making the universe accelerate. Is it truly constant or is it changing over time? We're looking for surprises in cosmic rays and other high-energy astrophysical phenomena, as well as doing experiments here on Earth, not only at the Large Hadron Collider, but precision experiments, testing gravity on very small scales, looking for violations of the weak equivalence principle, looking for new forces or laws of nature. So there's a multi-pronged attack where we're doing many, many different things. We hope to build a space-based gravitational wave observatory before too long. And you never know when the next surprise is going to come along.
Exactly, those are really searched in CMB. But unfortunately, we did not find those signatures yet. So far, yes. But the CMB is a place where the future experiment, we will not be able to improve that too much. So the fact that we have not seen so far, at least the signatures of bubble collision, the chance is not that large. Of course, there are some other signatures in CMB people studying, there could be, but as far as bubble collision is concerned, we will not be able to see directly. The chance is not that large. By the way, it is really important these signatures could tell us a lot of things. Suppose you see negatively curved universes. That's not just the suggestion of the multiverse theory. It would tell us how the fundamental level of quantum gravity may be working. For example, we talked about this box. Our own universe may be regarded as a box, and there is some boundary beyond which you cannot really see. But then the question is, if you cannot in principle see those regions outside the box, can you really say that that space exists? One picture is that yes, it does exist, has a big volume, big region outside our own something called horizon. The other picture is because we cannot even in principle see those regions, the formulation of the theory must be such a way that those regions really does not in some sense exist. It only effectively exists in the sense of extrapolating your picture in the horizon. And the negative curvature, you expect it to see only in the latter case. So if you see these signatures, you really learn something deep about the quantum mechanics of gravity, how to think about space and time, and what that really means at the cosmological scale where there are horizons. So these like tiny, really evidence from observations, you really have to interpret carefully what that really means. That's why, of course, theorists are useful. Otherwise, the experimentalists will do all kinds of experiments almost anyway. I mean, they don't need the suggestion from theorists. If they have technologies they will look into and they will do it. Sometimes not, but most of the case, that's the case. But how to interpret the result? Just only one or two numbers, curvature was negative, and this much, what that means? Curvature was there, great. No. You just can't say that this is a suggestion of the multiverse. It's not really proof, but it's a suggestion. And if that's the case, what that really implication at the deepest level? And you can really dig out those things.
There is a claim out there, Susskind and some of his collaborators have pointed out, the idea that if you measure the spatial curvature of the universe, so there's space-time curvature. Einstein says that general relativity gives us space-time curvature. So the very fact that the universe is expanding means that space-time is curved. But if you slice the universe into moments of time, so three-dimensional space, then you can ask the question, is that overall, on average, curved or flat? The observations tell us it's very, very close to flat. But they're not perfectly precise observations. There could be small positive or negative curvature. There's one way of getting a multiverse which says that you start with an inflating universe and you make little bubbles inside that inflating universe, bubbles that can bump into each other and form pocket universes all by themselves. If that's true, the curvature inside those bubbles is negative. It might be a small negative number, it might be very, very close to zero, so it looks flat. But if we someday detected a negative curvature to the universe, then you might say, oh, okay, this is what happened. We started with inflation, we had a bubble being created, we live inside that bubble. And you can't get positive curvature that way. But there are other ways to get positive curvature. If you have a baby universe that pinches off from the universe, from the bigger pre-existing space-time, then you will naturally have positive curvature in the universe.
Is that true quantum tunneling, the baby universe?
Yes, that is true quantum tunneling. And we don't know whether it's possible. You know, we argue back and forth. There are people who say, oh yes, this is going to happen all the time. There are other people who say we don't know, or no, it can't happen. It violates the laws of physics. So we should be very humble about what we know is true and don't know is true. I mean, it's quantum gravity in the early universe, right? This is not well-established physics by any stretch. So I would say right now, we don't have any way of saying whether or not you could get a positive or negative or flat curved universe.
Well, that's a very good question. We can assume that the entropy was low because of some theory of initial conditions that we haven't discovered yet, or maybe there's a deeper explanation that we'll discover someday. But to the extent that this question is related to the multiverse, I think one very definite connection is that we wouldn't have a second law of thermodynamics or an arrow of time that we actually observe if we didn't have a very large, big universe. So it's not enough to start with low entropy. You also have to have a high ceiling that you can grow to. And we know from studies of the connection between entropy and geometry that the amount of entropy you can have in a region of space depends on the surface area. It's proportional to the surface area surrounding that region. And we also know that that surface area is inversely proportional to the size of this famous vacuum energy we talked about, or the cosmological constant. And so if you had a universe, if we lived in a universe in which the cosmological constant had a large natural value, it would only be able to contain a few bits of information. To have a region that is rich in complexity and can have a lot of entropy growth, a lot of growth of disorder, you need a very small cosmological constant. And so you can see that to the extent that we have an explanation for a small cosmological constant, we also have an explanation for part of the problem of why there is an arrow of time.
The second law of thermodynamics says that entropy increases over time in closed systems. We think the universe is, to a very good approximation, a closed system. So entropy started out low, where by entropy we basically mean the disorderliness, the randomness, the disorganization of a system. There are more technical definitions than that. But basically low entropy means things are organized in very specific arrangements. High entropy means that things are more chaotic and disorderly. So our universe started in a very low entropy state, in a very organized, very unlikely state, where you'd pick a universe randomly from the set of all possible universes, it wouldn't look anything like what our universe started out like. So that's a puzzle. That's something for cosmologists to think about. Lots of people don't like that. It's a fact about the universe. So the question is, what is the explanation for that fact? There might not be one. It might be that, well, the universe just started that way. That's just a brute fact about the universe. Or, like I believe and like some other people believe, there's a deeper thing going on. There's something that we don't yet have completely worked out that explains why our early universe had low entropy. So here's one possible explanation. Maybe there was a pre-existing universe. Maybe our universe, the Big Bang, was not the beginning of the whole universe, just the beginning of our part of it. But maybe there was a pre-existing universe that had high entropy and that underwent a quantum fluctuation to separate out another little tiny universe that then expanded and grew into ours. A baby universe pinching off and going its own way from the bigger early universe. It's not really the same thing, because Penrose wants to have sort of one universe cycling over and over again. I'm really talking about a pre-existing universe creating a new one. So that there were one and now there are two universes. And the idea would be that it is easier to pinch off and start a small universe than a big one. So the reason why the new universe has a low entropy is just because it's easy to make low entropy universes to start than high entropy ones, because it's easier to make small universes than big ones. So it's possible that we live in the aftermath of this baby universe creation event, but then if that's true, we're not the only one. There's no reason to believe that would be the only universe that was created. There's probably many, many universes that are created. So that's how the multiverse comes into the game. Well, this is a great discovery in 1998 that the universe is not only expanding, but expanding faster and faster, accelerated in its expansion. And of course, it was a surprise. Most people didn't expect it to come along, and instantly you want to know why that is true. What is the explanation? Now, we have an explanation that Einstein invented back in 1917, almost 100 years ago, where he says that if space itself has energy, a constant amount of energy that is not zero, even in empty space, that would make the universe accelerate, exactly like we see. So that's the cosmological constant. It's also called vacuum energy. Sometimes people try to pretend there's a difference between the cosmological constant and vacuum energy, but they're really exactly the same thing. It's just the idea that space itself has a fixed amount of energy in every cubic centimeter. So that explains the data, but it raises a puzzle. Why is the value of the energy of empty space that particular value? If you make an estimate on the basis of quantum field theory, you predict that the energy of empty space should be much, much bigger than this number. So that's a puzzle. This is called the cosmological constant problem. Here is one possible answer to that puzzle. If the vacuum energy were as big as it should be, we wouldn't be here talking about it, because it would accelerate space so fast that you could not make stars and galaxies, much less planets and people. So there's what's called the anthropic principle. You can only observe and talk about the cosmological constant in universes where the cosmological constant is small enough to allow for the existence of life.
The same for fundamental constants.
The same for any constants, but the difference is that for other constants, it's hard to know what values they could take on to allow for the existence of life. For the cosmological constant, it's pretty clear. It could be bigger than it is today, but if it were much, much bigger, then we wouldn't be here talking about it. So here's one. So that doesn't really explain why it's small. That's just saying if it weren't small, we wouldn't be here. But if you imagine there's a multiverse, and if you imagine that in different parts of the multiverse, the vacuum energy takes on different values, maybe because we're in different compactifications of string theory, then there will be some parts of the universe where the vacuum energy is very, very large, some parts where it's very, very small, and life will only come into existence in the parts where it's very small. So there's an observational bias, there's a selection effect. We are only going to ever see those parts of the multiverse where the cosmological constant is small. So that's a very nice explanation if you believe that there is a multiverse with different values of the vacuum energy out there. And that would be a very direct tie-in to observational cosmology.
That process is pretty well understood as far as we believe. The process of creating bubble quantum mechanically is something called semi-classical process, which we believe general relativity plus some quantum mechanics, not in the deepest level, at the deepest level of quantum gravity, like a level we know and we can match, we can predict that that will happen. And the succession of that leads to eternal inflation, as you may have heard, like bubble is nucleated and then expand, and another bubble is nucleated and expand, but because expansion is faster than the expansion of bubble, this will lead to eternally bubble creating inflation. And that can happen also within our own universe. And so it can happen, like bubble can nucleate here, and that's probabilistically happen. But if that happens, of course, you will be immediately dying, so you will probably never notice. So we are automatically living in the probability branch that it didn't happen. So we probably won't be able to see and think that that happened. But it can certainly happen in our own universe.
And if you'd like to add anything on that.
There are two processes that I think are worth distinguishing from each other. One which we give the name eternal inflation, and another which we call vacuum decay. And they're in principle logically distinct from each other. And I think it's important to be clear how well we understand them. So vacuum decay is not very different both in concept and in how sure we are that we completely understand it from the decay of a radioactive atom. You simply have a state which has more energy than some other state that is available to the system. It's sort of like living in a valley that's higher up than some other valley. Now in classical mechanics, you'd have to walk over the ridge to get down to that more comfortable valley down there where it's warm and sunny. But quantum mechanically, you get to take a shortcut through the mountain and simply appear on the other side for a steep price, though, which is that it goes really slow. So you have to wait a long time in typical situations for that to happen. But calculating this sort of thing is been totally understood for about 100 years, and you can explain the rates at which various radioactive processes happen, for example, by doing such calculations. And really, there's a certain level of virtuosity you need to do this for empty space, going to a different configuration of empty space, which has lower energy, but conceptually, it's exactly the same thing, and we totally understand how to do this, and Coleman explained how to do this 40 years ago or 50 years ago. And it has nothing to do with quantum gravity or anything fancy that we don't understand. So it's completely under control. You can compute the rate at which this happens, and you can compute how it happens. It happens not by all of space suddenly converting itself to this lower energy. It happens instead by a small bubble appearing. And that bubble then grows and eats up the old high energy space in favor of making inside this new lower energy space. Eternal inflation is in principle something completely different. It's just a statement that it's possible to have a universe that grows at an exponential rate forever. And in fact, we seem to be living in such a region because we have what is called positive vacuum energy, and it seems to be quite long-lived because it's still around. And that's all you need for a universe that has that behavior, that its volume grows exponentially with time. But if you put those two things together, you get a really fun scenario where, every unit of time, in the case of our region, it would be billions of years, but never mind, some unit of time, the universe multiplies in volume by a certain factor, 20. And if the universe is a little bit unstable, to decay into a lower vacuum energy, then, after a while, in some of those regions that are being produced, it will in fact decay. And then this bubble will form and it'll start eating up the parent vacuum. But because the parent vacuum is inflating or expanding exponentially fast, it cannot catch up with that expansion, and so it'll actually only eat up a piece of it. Even if you wait for an infinite amount of time, basically the reproduction of the parent vacuum is happening faster than the eating up by the daughter bubble. And so somewhere else, the parent vacuum is going to decay again, maybe into a different daughter bubble, maybe it can have different kinds of daughters, and so on. And so then inside these daughter bubbles, if they still have positive vacuum energy, the process can continue, and so you populate this very rich, complicated universe that we call the multiverse. I don't think it's such a fully formed theory that it would make any such predictions. So one thing I can say is that loop quantum gravity is not trying to be a unified theory of quantum mechanics, gravitation, and all other forces and particles. It's trying to solve the problem of just putting quantum mechanics and gravity together. And so it doesn't even try to give you the kind of information about what the fundamental ingredients of matter are. But that has turned out to be absolutely crucial for the development that I described in string theory, where we saw that you can use those fundamental matter ingredients to basically figure out many, many different ways of getting empty space. So I don't think there could be any analogous structure in loop quantum gravity.
Loop quantum gravity is an alternative to string theory. As far as I understand it, it does not predict a multiverse. They're trying to simply explain the one universe we see, how gravity works in the world around us, in 3 dimensions of space, 1 dimension of time. Now, there might be versions of loop quantum gravity not yet invented that predict a multiverse, but it's not a natural thing that falls out like it does in string theory. Monopoles are predicted by some very popular theories called grand unified theories. The idea here is that electrical forces come in plus and minus, right? Plus for a proton, minus for minus charge for an electron. Magnets always have two poles, the North Pole and the South Pole. You never see a magnet with a North Pole but no South Pole. That's what a monopole would be. It would be a little magnet with a North Pole but no South Pole. You can theoretically write them down. Paul Dirac, the famous British physicist, did this. It turns out that just like the multiverse, in addition to sort of positing them and thinking about them, they are also a prediction. They're a prediction of these grand unified theories that try to unify the nuclear forces with each other. However, we haven't seen them yet. So in fact, one of the biggest justifications or motivations for inflationary cosmology was to get rid of the monopoles that grand unified theories predicted. In the naive, straightforward version of grand unified cosmology, the universe should be full of magnetic monopoles, and yet we don't see them here. So because we don't see them, that's a motivation for inflation. If you believe that this prediction is true and these theories are true, you inflate the monopoles away. So that's one of the reasons why inflation might be right. It's one of the good things about inflation. And once you have inflation, you arguably have a multiverse. Again, this is something that is still research in progress and we're not sure about. But in that sense, the quest to understand why we don't see monopoles has led us to believe in the existence of a multiverse. The sort of down-to-earth prediction is I think we will discover the dark matter. I think that is something that's very plausible to do. For the multiverse, I think we really just need to improve our theoretical understanding. And on the one hand, that's very hard because the data are not very specific. We don't have like data that we can't explain that are pushing us to invent new concepts. We just know that new concepts are necessary, and so that's much harder to make progress. But still, there's some low-hanging fruit. We don't understand quantum mechanics that well, much less quantum gravity. I'm a believer that getting the foundations of quantum mechanics much more firmly established will be immensely helpful in understanding quantum gravity and the emergence of space and time. That will help us understand the Big Bang, and that will help us understand the origin of the universe and maybe the multiverse.
Now I'm standing in front of Einstein's personal telescope, one of the greatest scientists in history, and reminding the story of cosmological constant Einstein had. That cosmological constant thing he introduced to avoid the consequence, a consequence of his theory of general relativity, that the universe has to be expanding or contracting. And in this situation, of course, he's no doubt intellectual giant. He really made a huge contribution to science. But even him, he really couldn't believe the consequence of his equations. And of course, later he said, oh, that was my biggest blunder. But even him, and that kind of example, a lot of example in the history of theoretical physics. Another giant called Paul Dirac, he's a giant, contributed a lot to the development of quantum mechanics. He had equations describing the property of electron, and that equation predicted that there must be some particle which has the same mass, but it's just the opposite charge. And of course, by that time, only particle known with a positive charge with the opposite of electron was proton. So he first tried to identify with a proton. Even him. Of course, later we found positron, that's an antiparticle of electron, exactly as his equation predicted. And the similar things going here, it's always human's mind. This was repeatedly happening. Now we have a general relativity or string theory. It may not be complete theory yet, but there is a suggestion that there may be some extra dimension whose complexity may lead to a lot of complex universes and so on. We again may not be able to just believe. That's wrong attitude. Okay? You should not believe. Okay? Believe may not be the right thing to do, but at least you should take things seriously and study the consequence. And if you really get to test these things in a scientific sense, that any consequence you draw from the theory is consistent with what you see. So it just reminds me that, of course, the greatness of Einstein, as well as that, we really think that even the greatest mind, you have to be open, you have to take seriously about what the equation says.